So, welcome everyone. Thanks for coming in person and also people connecting online. I cut it short, so I'm really happy that Andrea Del Prete is here. Andrea Del Prete did his PhD here in IIT. Actually, it was the first person that kind of I interacted with at IIT, and was the person that I was always going to ask any question I had because I knew nothing, so I needed to understand it. So. And then he did his PhD in IIT, then he went to LAS, then to Tübingen, and then now he's the associate professor at the University of Trento. So you may know him for the space inverse dynamics and all his contribution to robotic control. And today we do a presentation on his latest work on safe robot control, combining learning and model predictive control. So welcome.
Thank you, Silvio. Hi, everybody. Today I'm going to talk about safe robot control, as Silvio announced already. And before we delve into the details of the work, I want to give you some motivation of why I think that safety is a crucial aspect of robotics and why I decided to make it my top priority research subject recently. So there are, I think, two main reasons why I think safety is important. One is today, we have human-robot collaboration, mainly in industrial environments. One day, maybe this is also going to move to our homes, to hospitals, to other kind of less structured environments. And we want to make sure that this collaboration is safe, mainly for the human, but also secondarily for the robot. We don't want the robot to break or the environment to be broken by the robot. And this, I think, is pretty well known. And there are many people who are working on safety for this reason. There is a second reason, which I think is more projected into the future, which is the recent surge of high-performance black box data-driven control policies, mainly obtained through reinforcement learning algorithms. So these control policies are performing better and better. This is a result from DeepMind. But the problem is that we have no idea what's going on inside these policies because they are just huge neural networks. We don't know what they do. And so I think that if one day we want this to be really useful and to be applied in real world scenarios, we need some ways to certify that these policies can behave in a safe manner. And the work I'm doing in perspective, I think, could be used one day also for this purpose. So what is safety? You can define safety in many different ways. There is an ISO technical specification from 2016, which has been recently reviewed, which defines 4 different modes in which a human and a robot can safely collaborate in an industrial setting. I'm not using this definition of safety, even though I think that one day I will start using it. At the moment, I'm taking things in a maybe simpler setting. What I mean by safety is basically this list of things. So going from easier to harder, I want to ensure that the robot satisfies the joint angle, velocity, and torque limits. Those are like inner constraints of the robot. And I want to make sure the robot avoids collision, that being self-collision, collision with static obstacles of the environment. Typically, there is a table in front of the robot, there is a wall behind the robot, these kind of things. And also, of course, collision with dynamic obstacles, including humans and other robots. There is also a possible more advanced way of dealing with collision, which is collision management. So not avoiding collisions at all costs, but ensuring that if there is contact, it does not result in pain or injury. Of course, it is harder to define mathematically than the others. That is why what I've been doing so far basically is focusing on the first 4 points of this list, because everything that's in this red block, we can define it as an inequality constraint of the state and the control inputs of the robot. So this is very like a standard mathematical framework for dealing with constraints. This becomes already a bit more difficult because if you have a human in the loop, you don't know what the human is going to do. So you cannot predict the future behavior of the human. It becomes a bit harder, but I think once we have something that works well for these first items, I think I'm not afraid of extending to the latter. I think the real challenge is getting something that works well for the first items. And I hope I persuade you of that by the end of the presentation. So before I can tell you what we are doing, I need to get you up to speed with the state of the art. Maybe you already know, but who knows? So I'm going to do a quick review of the state of the art. So when it comes to safety, there are three main tools that you can find in the literature that allow you to certify that a controller is safe. Maybe you know one of them, but you don't know the other. So the first one is control-invariant sets. The second one is control barrier function, which is probably the most well-known. I guess who has heard control barrier functions? Okay, half of you. And the other one, which is I think the least known, is backup policies. The bottom line is that these three tools are actually very similar. So they are used by different communities, different sub-communities in robotics. And people who use CBF, they will tell you that CBF are the best and the others are shit. And the same is probably going to happen if you talk to people using the other tools. But my opinion is that these are almost equivalent tools. So it doesn't matter which one you use. They are just small variations of the same idea, the same concept. And my favorite one, for historical reasons, is control-invariant set. So that's the one I'm going to focus on for the rest of the presentation. But everything I say about control-invariant set, or CIS, applies basically to all the other two tools. Okay, so that's why I'm sticking with control-invariant sets. So let me tell you what a control-invariant set is. It's actually a pretty simple idea. So assume you have a discrete time dynamical system, x I plus 1 equal f of x I ui, and you have some constraints. So the state must belong to a certain set, so that it's a set typically avoiding collision, self-collision, collision with obstacles, joint limits, this kind of stuff. And also the control inputs are bounded because your actuators have a limited torque they can generate. We say that a set V is control invariant if once you are inside the set, it's possible for you to remain inside the set. Okay, so it's a set inside which you can remain forever if you want to. Doesn't mean you cannot leave it. You can leave it, but if you want, you can remain inside. So graphically, if this is the set of possible states X, we could have a control invariant set which is inside this X set. And typically you represent a control invariant set in this way, that you have trajectories that if they start inside, they can remain inside. Possibly they could start outside and get inside as well. That is not prohibited by the definition of control invariant set. Okay, so that's the definition. And it's not immediately obvious why that would be a useful thing to know, a control invariant set. But there is a very simple way that you can use a control invariant set to ensure safety for your controller, no matter what controller you have. And the reasoning goes this way. Suppose you know a control invariant set V. This set must be contained inside X, so the feasible states. And suppose that you begin operating your robot inside this set V. Then by definition of V, you know that if you're inside, you can remain inside V forever. It's possible. And hence, since you're inside V, you're also inside X, which is the space of feasible states, which means that you satisfy your constraints forever and you never violate them. So you have safety, basically. So in practice, this can be used in a model predictive control framework. Are you familiar with model predictive control? Raise your hands if you are. Okay, so I'm going to assume that you are. But very briefly, you're solving an optimal control problem inside your control loop. You just apply the first control input, and then at the next iteration, you solve it again using the current state as initial state of the problem. That's the idea. So the standard MPC formulation would be this one. And what you do is that you add as a terminal constraint the fact that your terminal state should be inside a control invariant set. And if you do that, then you can be certain that your MPC problem is going to be always feasible and you have safety basically guarantees. So the reason why this works, I'm going to try to persuade you with a graphical example. Suppose that you start at time 0 in this state x0, and you have a horizon of 4 time steps in the future. So you need to predict a future trajectory. That's what the predictive control does. And you have a terminal constraint on the terminal state of your horizon, which is represented by this red circle. So you predict a future trajectory, which may look like that. You apply the first control input, so you get to x1. And at the next iteration, you start from x1. And again, you predict a new trajectory, which must end after 4 time steps, again, inside that control invariant set. And you keep doing that over and over and over. And by definition of control invariant sets, you can be sure that this trajectory always exists. Because if you were here, you know that you can remain inside here. So at the next time step, you can still satisfy that constraint. You can never find a problem that is unfeasible by definition. And so you keep doing that forever, and you're happy, you're safe, everything is fine. So that's basically the state of the art. Can anybody guess what the problem is with this approach? What's the gap between theory and practice?
What if a disturbance came in and kicks you out from the mix such that the...
That's a concern, but that's quite easy to fix using robust methods, which I'm not going to talk about because, again, I think the challenge is not there. Even in the case of perfect model, what is the problem with this approach? Can you find any?
The fact that the window that you have, you need to always be inside to reach the terminal constraint, basically.
Yeah, but if the terminal constraint is control invariant, that's not a problem.
Maybe in the window that you have, you cannot reach it. Because you have constraint on.
But if the assumption is that you start already inside the set, so x0 is already inside the set, so you can always remain inside it.
Okay.
I mean, as in most cases, the problem between the gap between the theory and the practice is the assumption. I'm assuming that I know a control invariant set. Okay, but how would I know a control invariant set? Control invariant sets are unknown for most dynamical systems, especially nonlinear ones. If you have a linear system, then there are tools for computing control invariant sets, as usual. Linear systems are nice. All the theory has been developed for them. But now we are left with the nonlinear stuff, which is hard. So what people do in practice is that they use numerical approximation techniques to find numerical approximations of control invariant sets. And the issue is that you get an approximation, you don't get a control invariant set. So would an approximate control invariant set give you any guarantee? No, because it's approximate. So you lose, the theory basically drops at that point. And also they are computationally demanding to compute. So it's not only that they are approximate, but it may take you weeks to compute one such set. So can we do something having an approximate control invariant set? And for as much as I've looked into the literature, there is no answer to that question. So you can find books after books after books saying, okay, assume you know a control invariant set. And then they spend hundreds of pages proving all the nice properties that your controller can have under the assumption, but it starts from an assumption that is unrealistic, in my opinion. There is no way you can guarantee that your set is control invariant. So I think we need to relax that assumption, start from something a bit more reasonable, and try to prove properties based on that. So my very ambitious goal today is to present two contributions. I haven't started yet, like you noticed, so it's ambitious. The first one is a paper we published on RAL last year. It's this one, which focuses on computing a control-invariant set for robot manipulators. Robot manipulators are kind of a good starting point because they're a bit easier and lower dimensional than more advanced robotic systems like humanoids. And also they have some properties in terms of their dynamics, which we were able to exploit to make the methods more efficient than the state-of-the-art methods for computing these control-invariant sets. The main problem with this approach, I'm going to tell you up front, is that it is tailored to fully actuated system. So humanoid is not fully actuated, quadruped is not fully actuated, quadcopter is not fully actuated, vehicle is not fully actuated, underwater robot is not fully actuated. I mean, you know it, right? But if you're working with a manipulator, I think this is a very good method to use. And then the second contribution, which we did even more recently, it's just been accepted at ICRA, to be presented in May. It's a method that can use an approximate control-invariant set without the guarantees that this is really a control-invariant set, and still give you some guarantees about safety of the resulting controller. And this is not tailored to manipulators. So this is generic. It applies to any dynamical system which is differentiable. If it's not differentiable, you cannot use MPC, basically. So it's tailored to MPC. So as long as you can use MPC, you can use this method to get better results using your approximate control-invariant set. So since I am afraid I'm not going to be able to show both of these today, I'm going to start with the second one, the one on MPC with approximate control-invariant set, because that's more generic. It's also more recent, so I'm more eager to present it. And this is joint work with my PhD student, Gianni Lunardi, Asia, who was an intern. She did an internship with me, and Matteo Savariano, who is a colleague of mine, is an assistant professor at the University of Trento with me. So the method is called receding constraint MPC, and you will understand why we gave it that name in a moment. So let's start again from what we saw is the state-of-the-art approach. You do a standard MPC, and you just add a terminal constraint to be inside this set V, which ideally would be a control-invariant set, but in practice is not a control-invariant set. It's an approximation of a control-invariant set. That's why I added a hat on top to say that it's approximate. So is that a problem that you have an approximate control-invariant set? Yeah, it's a problem. So suppose this is a real control-invariant set, V, in green. And suppose that you're given an approximation, which may look like that. So what could happen is that you start inside this approximate control-invariant set x0. You predict a trajectory going into the future until xn. N is the size of your horizon. Then you move to x1. You keep predicting. You go to xn plus 1. Then you move to x2. And when you try to predict until xn plus 2, you realize that you can no longer remain inside V hat, because it's not a control-invariant set, it's an approximation. So if you're here, you cannot remain inside the red set. You must leave it. And at this point, your problem becomes unfeasible and you're screwed. You don't know what to do. Okay, so that's the issue with having this approximation. So our first idea was, instead of assuming that we have a control-invariant set, let's simply assume that we have an inner approximation of a control-invariant set, which is a much more reasonable assumption, I think. It's much easier to guarantee that you have an inner approximation of a set rather than you have exactly that specific set that you want. So if you have an inner approximation, it means that any state inside the inner approximation is also inside the original set, which means that it's safe, because all the states that are inside V are safe. So what you can do is that if you detect that your problem becomes unfeasible, because you can no longer remain inside V hat, what you can do is that you can simply basically stop the task that you're doing and switch to a safe task abortion procedure. And the way we do the safe task abortion is that we start from the very last state that we predicted, which is still inside the set, V hat. And from that state, we try to find a trajectory that reaches an equilibrium state. So a state in which you can remain forever just at equilibrium. And since we know that any state inside V hat is safe, we know that that trajectory does exist. The only thing you need is to have at least 2 computational units on your machine, because one is going to keep basically tracking the predicted trajectory, while the other one solves a trajectory optimization problem to find this safe abort trajectory. So going back to the graphical example from before, you are in x2, you try to predict until xn plus 2. You realize that this is not possible because you would violate the terminal constraint. So you start the safe abort. You start the safe abort, but not from xn plus 2, because that would be outside the hat. You start it from xn plus 1. And from that state, you try to find a trajectory that leads you to an equilibrium state.
But isn't that PC responsible of avoiding violating the terminal cost constraint to be out of the...
Yeah, but if it's not feasible, it's not feasible. I tell you x greater than 1 and x smaller than 0. Okay. It's not feasible. And so from this state, you find this trajectory, while in parallel, you keep following the trajectories that you predicted until xn plus 1. And if you did your things correctly, you should have solved this trajectory optimization problem before you reached this state. And so once you reach this state, you have already this trajectory which you can follow to get to a safe equilibrium state. Okay. I think it's a quite simple idea, nothing revolutionary. And this is enough to ensure safety. So you do your task, and if you detect a problem, instead of like miserably failing, you switch to this safe task abortion, which means that you gracefully stop what you were doing. So it's not great because you didn't achieve the task, but at least you didn't break anything. Okay. Even better, it would be to ensure recursive feasibility, right? Recursive feasibility, it means that you can keep doing your task without stopping it. That would be the ideal goal. And we have also a second idea that goes in that direction, but it's a bit more complicated. So the idea starts from this quite simple observation. The standard MPC approach is to ensure that the terminal state of your prediction horizon is inside this control-invariant set. But actually, if you think about it, there is no reason why it should be the terminal state. Why not the state at time n-1? That would be fine too, because you can reach that state and be safe. Why not at n-2? There is no reason. There is a reason, but let's pretend there is no reason. I mean, my point is any future state being inside a safe set is sufficient to ensure safety. That's the key point. Because you can reach a state that is safe, and from that point onward, you're fine, theoretically speaking. So the idea is maybe we can adapt the time step for which we enforce this constraint. It doesn't need to be always the very last one. Let me show you what I mean by that. So this is our standard setting where we have a terminal constraint, and we start by predicting a trajectory that ends inside this terminal set. At the next iteration, we know that the standard approach would be to have also always the constraint on the terminal state. But we have seen that if this set is not control invariant, which it is not, unfortunately, in practice, having this constraint would make the problem unfeasible, because maybe even if you were inside the set here, you cannot remain inside it, as we saw in the example from before. So our idea is, well, I know that maybe I cannot be inside the set at time step 5, but I know that I can be inside the set at time step 4 because I already computed a trajectory that reaches the set at time step 4. So if at the next MPC loop, I shift my constraint backward in time, so I make it recede, that's why it's called receding constraint, then I can be sure that the problem is feasible. I cannot lose feasibility if I do this. And I can keep doing it for a little while. So I shift it to time 3, then I shift it to time 2. But the problem is that eventually I run out of my horizon, because once I reach the very first time step, I can no longer shift it back. So this is fine for a few cycles, but it's not good enough to keep you running in the long term. So we need to add another ingredient to make this work, which is a soft constraint. So we have the hard constraint, which is receding over the horizon. But then we introduce also another constraint, always to be inside the same set. So the color are different because this one is soft and this one is hard. A soft constraint is a constraint that can be violated by the solver if it doesn't find a solution that satisfies it. But if there exists a solution that satisfies it, then the solver is going to satisfy this constraint. Okay. So we have a hard constraint that recedes in time, and a soft constraint that is always at the end of the horizon. So the soft constraint can be violated. For instance, there it is violated. Even in this case, it's going to be violated. But eventually, with a bit of luck, it may be satisfied. And when it is satisfied, you know that at this point in time, it's possible to satisfy the constraint. And then you can move the hard constraint forward in time. And this allows you to keep going potentially forever. Okay, so this is the high-level idea. To be a bit more mathematically precise, what we were able to demonstrate is that if your constraint set, the hat, well, is an inner approximation of a control invariant set, and it is actually an n-step control invariant set, then you have recursive feasibility. What does it mean, n-step control invariant? This is something that we created. We didn't find it anywhere in the literature. It means that if you're inside this set at time 0, then it is possible that at a certain point in the future, you will be again inside the set with a k between 1 and n. So you can come back to the set in at most n time step. So it's a weaker requirement than standard control invariant set.
But if you go outside the set for just those few points, aren't you therefore unsafe for those?
No,
few points?
no, it's fine. It's fine because I'm implicitly assuming that even if you go outside, you never leave X, which is the feasible state space. Because the MPC problem guarantees that all the states are inside X. The problem is more what happens after the horizon. Okay, so as long as you can come back to the set in at most n time steps, then your n-step control invariant. And if you're n-step control invariant, then the MPC scheme that I just explained gives you recursive feasibility. So basically, we have recursive feasibility, which is the best property we could hope for an MPC scheme if we want safety, but under a weaker requirement than the standard approach. So yeah, I think it's a win. And the formulation is not that much more difficult than the standard one. You just have two constraints instead of one of which is soft and one is hard. So in terms of coding it and computation time, it's kind of the same. So I think that without adding much complexity to your scheme, you can have a much higher chance of having recursive feasibility, because this requirement, I think if you have an approximate control invariant set, it's quite likely that it's going to be n-step control invariant if n is large enough. Of course, the larger n, the easier it is to satisfy this property. With one-step control invariant, we recover the standard definition. So that's the strictest one. So again, graphical example. I think this doesn't add much. Basically, with this new scheme, you can temporarily leave your terminal constraint set, which is this red set, because you can violate the soft terminal constraint that's allowed, as long as eventually you go back inside the set. For instance, in this case, I was optimistic. You just go back after leaving for one time step. You could stay outside the set for longer. Up to n, it's fine. Okay, some results. We compared 5 different MPC formulations, one of which is our receding constraints MPC formulation. And we used a 3 degrees of freedom robot manipulator. We use a.k.a. as a software library for coding the MPC framework. And the task we tried to achieve was a set point regulation, starting from random initial states and trying to reach this reference configuration, which was very, very close to the joint limit for joint 0. So we are just basically 1 degree of distance from the joint limit. So it's very difficult, because if you overshoot just by a little bit, you hit into the joint limit and you violate safety. And we used slightly different horizons lengths between 34 and 36 for the different formulations to ensure that we have always a computation time which is smaller than the time step, which was 5 milliseconds. So if for instance, our MPC scheme is slightly more computationally demanding than the standard one, so to compensate for that, we use a slightly shorter horizon so that the comparison is fair. And all our code is open source. You can find it on GitHub if you're interested. So this table summarizes the results. So these are the 5 MPC formulations that we tested. Naive is basically a naive formulation without any terminal constraint. Soft terminal is a formulation where we have only a soft terminal constraint. Here we have a soft terminal constraint, and we also trigger the safe abort procedure when we detect that this constraint is not satisfied. Here it's the same, but using a hard terminal constraint, just to check if they produce different results, and they slightly do. And the final one is our own, so the receding constraint MPC. And here I'm reporting the number of tasks that have been completed. So you got to the point that you wanted to reach. The number of tasks that have been aborted safely. So you have to stop and do safe abort. So you don't complete, but at least you're safe. And this is the number of tasks that have failed. So you violated a constraint. And so let's look first at this column. The number of completed tasks, it's basically the same for the first 4 formulations, whereas our formulation achieves 7 more tasks out of 100. The number of tasks safely aborted, well, it's none for these 2 because they don't have the safe abort procedure at all. And for these ones, it's 11, 8, and 18. So we are able to safely abort more cases. And probably the most interesting column is this one. So how many times did you violate the constraints? 30% basically for the first two, 19 and 22% for the third and fourth, and our violated the constraint only 5 times out of 100, which is still high. But I mean, we designed the task to be really to stress test the formulations, of course. So the cost function and the target set were explicitly chosen to maximize the number of constraint violations. So I think in a standard setting, this would probably go to 0. We could make it safer by restricting our terminal constraint set to shrink, by shrinking it. Because of course, the smaller the terminal safe set is, the higher the chance that you have an inner approximation of the control-invariant set. So here, basically, starting from the set that we computed, we shrinked it by 2%. That's the safety margin. Then we tested it with a 10% safety margin, and we went from 5 failures to 3. So indeed, if you take a smaller set, you can reduce the number of failed tasks. This, of course, applies also to the other formulations. But this one remains always the best one. We can also take a look at, okay, this is safer, but what about performance? Is the cost increasing a lot for this extra safety? So compared to the naive formulation, the percentage of cost increase, you can see it's very, very small for all the formulations, actually. So we are talking about smaller than 0.1% of cost increase. So performance is basically the same. So the extra safety that you're getting is almost for free. And in terms of computation time, we can check that almost all the formulation have a computation time below 5 milliseconds. The only one who didn't was this one, but we are only slightly above, so I think it's fine. And you can see they're very similar. So the naive one, which is without any constraints, is only slightly faster than our. We are using a shorter horizon to compensate for the extra computation cost. But in practice, I think this is pays off. The only issue is this safe abort computation time, which is the time that it takes to compute the trajectory to reach an equilibrium state, because that's a completely from scratch trajectory optimization problem that you need to solve in parallel to your MPC controller. So first of all, you need 2 computational units. So at least your machine needs to have 2 cores, which is, in practice is not a big deal. And even under that circumstances, you can see that the computation time here is quite long. So we're talking about 100 milliseconds more or less. So you need to start doing this computation well in advance, and you need your horizon to be sufficiently long. So here we didn't use any warm start technique. I think that if we were to implement some warm start techniques, we could probably reduce by a lot these numbers. And that's actually the main bottleneck why we are not testing it on hardware yet, because we need to reduce this number to apply it on hardware.
Sorry, but the point where you start the safe abort would be different. Whenever you notice there should be a safe abort happening, you start optimizing early on. Then keep optimizing, but that point will be different.
No, because at that point, basically, you stop solving the MPC problem, you just track the last solution that you have.
Okay.
So you no longer optimize, but you still need a computational unit for taking care of the tracking.
Okay.
Okay, so as I was saying, what we are working on right now is to find a way to warm start the safe abort OCP, because right now it takes too long. And in the future, we could use robust optimization to handle dynamic uncertainties, which is what Michele was saying. So right now, we are assuming that our dynamics is perfect, so everything is going to go according to our model, which is not the case in practice. But I think that this extension is not really critical because we have robust model predictive control techniques that work quite well. So you can account for uncertainties. And this same machinery, I think it could be very easily applied to make a black box policy, maybe trained through RL, safe by basically acting as a safety filter in sequence to the black box policy. Another area of interest is computation and certification of sets that satisfy our assumptions, because right now, even if you have weaker assumptions than the standard one, they are still strong somehow. I mean, we have currently no way to certify that our set is an inner approximation of a control-invariant set, or that we have an n-step control-invariant set. This is even more difficult to certify. So we need to work on that area. Okay, so as I predicted, I am already out of time, so I'm not going to present the second work. So let me just skip. So this was the second work that I wanted to present to you in an ideal world. You can check it out. It's published in RAL last year. If you're interested in how do we get that V hat set that we use as a receding constraint in that work, well, we computed it using this method, which is a method that uses trajectory optimization and neural networks to compute an approximate control-invariant set. Okay. This is tailored for robot manipulators, which makes it more efficient than state-of-the-art methods for computing control-invariant sets.
And you're sure that it's an inner approximation?
No. We just compute it and then we shrink it by a certain percentage. So I told you either 2% or 10. And the more you shrink it, the safer you are. But this is going to affect the number of tasks that you complete, possibly. So you reduce the number of completed tasks, but you reduce the number of failed tasks. It's a compromise. So in conclusion, I should have presented you a complete framework for safe control, but I didn't. I only presented you the second part. The first part was the learning of the set. The main limitations that we currently are facing is that the algorithm we have for computing the safe sets, even if it's better than the state of the art, it still scales exponentially with the size of the problem. That's why we're working with a 3DOF or at most a 4DOF manipulator, because it takes hours to compute these sets, even for such a small system. And that's a problem that's common to all the algorithms in the state of the art for computing these sets. It's not a single problem of our approach. And yeah, as I was saying before, we are also working on the certification of properties such as inner approximation and step control invariance. What gives me hope is that it's very easy to show that computing these sets is equivalent to computing the value function of a specific optimal control problem, where your cost function is simply the violation of your constraints. It's a penalty on the violation of your constraints. So if you formulate that optimal control problem, the value function basically gives you the set. You take the zero sublevel set of the value function and you have that set. So if people are able to solve optimal control problem with RL for very large scale systems, my hope is that we could maybe use the same tools to compute these sets for very large scale systems. I wasn't able to do it yet, but that's my hope for the future. Okay, I'm done. Thank you.
So I guess we have some time for questions. So I guess we have a question on the cloud. Otherwise, if I don't know, Chang, if you are connected, was your question answered by Andrea in the presentation, or you?
No. So I noticed that so in when Andrea introduced the soft constraint, I'm wondering, like, what if we are unlucky to satisfy the soft constraint even after n steps? because as I understand, if I understand it right, so the soft constraint is like an indicator for restarting the hard for moving the hard constraint back to the end of the prediction horizon, right?
Yeah. So if
So, like,
you, yeah, I mean, it happens in our tests. Those are the failures, basically. The 5 failures that we have seen in the first experiments. Those are basically cases in which what you're saying happened. So even after receding our hard constraint for n times, we get to a point where the soft terminal constraint was never satisfied. And at that point, we have to switch to task abortion.
okay.
So that can happen, but if that happens, it means that your set is not n-step control invariant.
Okay.
Which
thanks.
indeed, I mean, we have
that.
way to certify that it is, so it can happen. I mean, it did happen.
Okay. Yeah. Thanks for the answer. Thank you.
You're welcome. So either that, or it could possibly also mean that even if your set is n-step control invariant, your solver is not just good enough to find the solution, even if one exists. Because everything we're saying is about existence of solution. We are not talking about the ability of the solver to find a solution if one exists. We are taking for granted that the solvers are good enough, which is a big if.
Okay, clear. Thanks.
Thanks to you.
Okay, I don't know if there are more questions also in the physical audience.
I have a question. So first of all, thank you for the presentation. And I connect to what Cheng was saying about the n-step control invariant property. Do you think it's a property of the approximated set, or that holds always, or is something that can be task dependent?
So the beauty of all this machinery on safety is that it's task independent. It just depends on the dynamics and the constraints, which typically are always the same. I mean, you always want to avoid collision, and the dynamics of your robot is always the same. So even though computing this set takes weeks, you just do it once, and then you're good, regardless of the task that your robot is trying to achieve. And about making sure that you have this n-step control invariance, at the moment, we have done nothing to try to ensure that, because it's something that emerged during the development of the second work. So it was just after doing the first work on learning the set. So now I would like to go back to the work on learning the set and try to learn a set that satisfies this property. But it's very difficult with neural networks, because basically, even though you're feeding the training algorithm with points that are all satisfying a certain property, you know that in between data points, the network is just approximating. So to make sure that the inner approximation that the network does still satisfies the property you would like, that's a bit tricky. I mean, it's not impossible. There are work that are doing that are based on robust optimization, Lipschitz constants, these kind of tools. So I have a new postdoc who just started in January that's probably going to work on this, and I'm hopeful that we're going to get something by the end of the year.
Okay, thank you.
Thanks to you.
I don't know if there are any other questions.
I have one question. So if you have this n-step control invariant set that is inside, suppose your control invariant set, anyway, even if you have this n-step, it doesn't mean that you will always remain inside the control invariant set, right? Because during those n steps, you might go outside, since you don't know which is the right control to apply when you're outside the n step one, while inside the big one, keep it inside. You still might get unsafe, basically. In the meantime, let's say.
Yeah, I mean, you can have like the tail of your predicted trajectory, which goes outside, but you're always going to maintain one state of the predicted trajectory, one like a intermediate state inside the set. And that is enough to ensure safety, because you know that from this inner state, you can always do a safe abort and reach an equilibrium position, equilibrium state.
So you would do that even in an end step one.
Yeah.
Okay.
Yeah. I didn't say, but even our receding constraint MPC does the safe abort when we fail to satisfy the constraint at a certain point. The problem is that with the receding constraint MPC, the safe state recedes during along the horizon, and so when you trigger the safe abort, you have much less time to find the trajectory. That's why we are working on making the safe abort problem faster to solve, because with the receding constraint, we have much less time to solve it. So yeah, we're working on that. Thanks. Well.
Just a question in the audience or also remotely, people from the cloud, if they have questions.
When do you trigger the safe abortion in case of the receiver saying? You trigger it when the soft constraint fails, or?
I trigger. So what we did in the experiment is that we trigger when we have the receding constraint, which is at time step 1 of my horizon. If in that case, the soft constraint has failed again, is violated again, I trigger the safe abort, which means that I have 5 milliseconds to solve the trajectory optimization problem, which is, I think, not very realistic. But actually, you don't need to wait until the very last moment. You could trigger it before. And when you trigger it, depends on how much time do you predict it will take you to solve the safe abort problem. So right now, yeah, we are trying to make the safe abort as fast as possible. And then based on that, we're going to decide when we trigger the safe abort. Realistically, I think it's going to be at time step 4. So we have a horizon of 34, which means we have 30 chances of satisfying the soft terminal constraint. If after 30 times we fail, then we trigger the safe abort and we're done with it.
But do you manage to solve it in under milliseconds?
So now it's taking...
knots are under milliseconds of trajectory?
No. 4 knots are 20 milliseconds, because each knot is 5.
Okay.
And right now it takes 80, but I think we can get it down to 20 by using warm start.
Okay.
Yeah. Because now we are solving it from scratch. So of course it takes tens of iterations, but with a good warm start, we can solve it in 3-4 iterations. So yeah, that's my hope. But all the computation times I've been showing, they are not average. They are 99% percentile. So basically, these are worst case scenarios.
Okay, I don't know if you have any other question. I have one. You mentioned before that constraints remain the same as long as you have static, let's say, object in C, right? That's why. I mean, the first thing that you mentioned that why you don't want to do dynamic.
No, I think you can apply the same reasoning also with dynamic constraints. You just need to formulate it in a smart way. For instance, you can say that you model like a ball around the end effector of the robot, for instance, and this ball has a dynamic radius, and you change the radius of this ball depending on your sensing. So when you sense humans that are far away, you have a large radius, which allows the robot to move very fast inside this ball. When humans are getting closer, you just reduce the radius of this ball, and you're going to encode your set using this radius as a state, basically, of the robot, as an extra state of the robot. So you can still learn the set once and have it work for any dynamic obstacle that is environment. This is kind of already done in the state of the art. So yeah, I will take that and apply it here. Of course, it increases the size of the state, but if you use a ball, it's just one variable, so it doesn't change a lot. If you want, some people are using like laser beam measurements to detect, so basically they augment the state by measuring the distance to obstacles in an array of directions around the robot. That would be a lot more expensive because you might have, I don't know, 20 extra states. But if you use a single ball, you have just a few, or you can use a box, and then you have like 6 variables for representing the box. It's up to you.
Okay, thanks. I think we have later 1 minute. If we don't have any more questions, we can also make them offline. It's not a problem. So let's thank again Andrea for the presentation.